Today we're going to be working on another Amazon's interview question. This is Leetcode question number 52. This is N Queens part 2. So this time, instead of actually sending the positions of the queens in an N cross N chess board, we're just gonna return the number that how many solutions are possible. So in this case, when n is equal to 4, as in the previous question number 51, we did see in the last video that there were two solutions, but we were returning arrays or strings in order to display the location of the queens. This is a hard question. I'm gonna try to, it's a very small code, but like very hard to understand. So as I go through this one, we'll talk about it. Yeah, so a couple of things. Let's just start with the complexity here. The thing is that in terms of the space complexity, it's gonna be a linear one. At most we can have like n number of elements in in these different sets, right? Okay, and in terms of like, yeah, so I think the upper bound is gonna be n cross n. Okay, I'm just wondering if it is O of n or O of n square, because we can put only n number of columns inside the occupied one, and then we can actually have a little over n in the diagonal ones, and the occupied diagonal 1 and occupied diagonal 2. So we can have that. So we cannot actually at any point in time, we're not gonna be putting the whole n cross n number of elements inside any of those. So I think it is safe to say that the space complexity is just linear, not even just like the n cross n linear. It's a little more than n, but still it's just like we need, at most we're going to be saving O of n elements in these sets. And again, we are not considering the stack, the call stack space in here. Okay, that being said, so if we do consider the like over here too, like the call stack too, as we can see that we're gonna be going through all the ones, and that's however many times we're gonna be calling this helper function. So we can say that the space complexity of O is gonna be O of n square if we just consider the the call stack too. Okay. Now, in terms of the time complexity, we're going to be going through the n cross n matrix once, and that's it. Like, because we are not doing anything. The last time when we had to show the positions, we came up with the complexity of O of n raised power 4, but this time it's just gonna be O of n square, as we are just gonna be going through every single thing once, and that would be it. Okay, we have three sets. We chose the data type as sets because we want to make sure that the location of the columns, or this diagonal 1 or diagonal 2, is going to be a particular integer, and we're just going to be going through. So basically the columns is going to be the number of the column, and the diagonal we will go through it what those are, but those are also going to be integers, and we just need a set for that. And int count is equal to 0. We're going to initialize our count equals to 0, and then we're going to call a helper function with 0 as a row, and the n is like how many like what is the size of the n cross n chess board, and that's going to return us the answer. The way we're going to be doing it is like we are going to be sending the row, but then every single time we're gonna have our column go from 0 to n, like we're gonna go through all the columns in here, right? And then we're gonna have three calculations. Those column, they shouldn't be in these occupied column set of integers. The second thing which we're gonna calculate is row minus column, and the third thing is gonna be the row plus column. Row minus column is gonna be called diagonal 1, and row plus column is gonna be diagonal 2. Very non-intuitive. It is not like we are saving the indices, like the indices of rows or columns. It's just like it is. We're gonna be going through the pseudocode here in a second, but just remember that when looking at a particular location on the chessboard, if we have, in order for us to detect that there is no such thing, no element or no coin in the same diagonal, you can actually see that whenever you do a row minus column, maybe the row is second and the column is 1, and the the difference is going to be 1, and then the row is 1 and the column is 0, the difference is again going to be 1. That would actually eventually mean that there was another coin which was on the same diagonal. Same goes true with the rows and the columns, with the addition of that. So if you have a row 2 and a column 3 and you add that number, right? So that would be, so what actually happens here is just like now you would think that, okay, I have a row 2 and a column 3. That would make it 5, right? So basically, while sitting on row 2 and the column 3, you have calculated a diagonal which is equal to value 5. When you will come across, when you will go through the iterations, and later on when you will see that, uh, when you will see that uh, the 7 has been added before, right? So think about this way. We were at a position where the row was second and the column was third, right? So that would, the addition would bring it to 5. But then we can be in a situation where the column was 3 and the row was 2. That would again make it, so let's talk about it. So row 2 is this, and column 3 is gonna be this. If you see my mouse, it's gonna be this one. Now the column 3, sorry, row 3, 1, 2, 3, and the column 2 is gonna make it here. Did you get that? So that is the reason the addition would cover the diagonal going from, how should I explain, from the top right to the bottom left, and the subtraction is gonna cover the column from the top left to the bottom right. So that's how we're gonna be covering these two different diagonals, that the queen cannot be placed in one of these diagonals. So again, we're gonna go through, if you have seen that column already inside that set, or you're gonna continue, you don't want to consider that column. Again, if you have seen that diagonal 1's value in the occupied diagonal set, you're going to continue. Again, if you have seen diagonal 2 in the occupied diagonal 2 set, you're going to continue. And the last thing is the moment when we're going to be adding that particular row, sorry, we're going to increment our counter when the row is the last row. If you have seen, if you are at a point where you have gone through all the rows and you are on the last row and you calculated the columns, right, and they are not already inside these sets, the column set, the diagonal 1 set, the diagonal 2 set, that means you hit a pot, like a jackpot, and that means that this is the solution and you need to increment the counter. Otherwise, most of the time we're going to be hitting this else, where we are adding that column to that column occupied, adding diagonal to the diagonal occupied, and adding diagonal to the diagonal to occupied diagonal 2, and calling the helper function again, uh, row plus 1, right? And then removing all of them one by one, again as we do in permutation or combination, adding an element, incrementing with a helping, calling the iteration again, calling the helper function again with an incremented count index, and then removing the same element. Okay, I can go through the pseudo code again. It won't. So we have these three things as empty at the beginning. You are starting with the helper function 0 to 4. You're gonna be going through, your columns are gonna be going through from 0 to 3. Column 0 is gonna be the first one. Subtracting and adding them is gonna create 1. Then you're gonna call the helper function again. This time at the end you're gonna be adding these zeros in there. Then you're gonna be calling the helper function here again. Now the column is gonna again start from 0 to 1, and then these are gonna be the, because the row has been changed now, right? And the column always start with that. So maybe it was 0 1 minus 0, which would make it 1, and this is 0 plus 1 is 1, so that would go in there. And so I think it is less intuitive how it works, but just remember that the column is the one who is looking for the any duplicates in the columns. The diagonal one is looking for any duplicates in the diagonal starting from the top left to the bottom right, and the diagonal 2 is the one looking for any duplicates in the diagonal starting from the top right to the bottom left. We already talked about the complexities here. That's all I wanted to cover in this video. Thanks for watching.